Namaskar, a very good afternoon to you all. So, myself, Manu Mehta, faculty with photogrammetry and remote sensing department, and I'll be discussing with you an overview of remote sensing. All right, so good to go. Uh, to begin with, there are principally two methods to collect any scientific data. One, you go to the ground, go to the field, take your instrument, take the measurement, and this is called in situ measurements or field measurements. These are more accurate because they are directly in contact with the object. So, but this is not always possible for you to go and take the measurements on the ground every time. So another method for you is to remotely sense the data, sitting at your place, taking the information from a sensor, which is remotely sensing the information from the object. So today we'll be focusing more on the remotely sensing method to collect any scientific data. So we'll first try to learn the answers to the three basic questions. That is what, why, and how of remote sensing. So coming to what remote sensing is, it is both a science as well as an art. Science because it is based on all the scientific principles to acquire and gather the information, and art because it depends on the skill of the interpreter, how he or she interprets the information obtained remotely. So the science and art of obtaining information of three things: an object, let's say you have a feature of interest, let's say a building, or an area which can comprise of several features at a time, let's say a city, or phenomena, something which is happening, say rainfall, any disaster, etc. So the science and art of obtaining information about object, area, or phenomena through the analysis of the data acquired through a device which is not in physical contact with the same. Okay, so you're gathering the information from a distance essentially about any of these three, an object, area, or phenomena. This is the remote sensing part of it. So right now you're all looking at the screens and getting the information, so your eyes are acting as your remote sensors. Then comes the why part of it. Why should one go for remote sensing? One reason I just mentioned in the very beginning, that is, it's not possible all the time to go to the ground and collect information. So sometimes the area becomes inaccessible. So that time it is the only solution. But otherwise also, remote sensing allows you to have a systematic data collection. If I'm sending 10 people to the ground to collect 10 samples, so 10 samples in 10 different manners you might be collecting. There might be 10 different types of errors that may be cropping up. So there will be a subjectivity in the data collection. To avoid that, here you have a systematic data collection in a particular proper fashion. These days, you all must be having information on Google Earth, and some places are having three-dimensional information also. So three-dimensional information of real objects is also available. Repeatability in terms of space as well as time. You can cover the same area after every 10 days or 10 months or 10 years, depending on what type of platform and sensor you're looking at. Then global coverage is definitely a very good application of remote sensing where you can have a synoptic view of the data and a global coverage of the data in a very small amount of time. As I said, it's the only solution sometimes for otherwise inaccessible areas. Like suppose there is a disaster, can't visit the area at that particular time, but remote sensing is the only solution that time. Now, the same information which has been collected through your sensor can be interpreted differently by different application groups, be it forestry, be it geosciences, be it water resources, etc. So it serves as a multi-purpose information to you. So having known the advantages of remote sensing, should you do away with the ground measurements? No. As long as remote sensing survives, the field measurements have to survive because number one, for accuracy assessment, whatever you have acquired using remote sensing, whatever you have analyzed using this technique, you have to cross check how correct you are. So, for accuracy assessment, we are still dependent on field measurements. Also, for calibration of the remote sensors, before you fly them on the board, you have to first calibrate them with respect to field measurements. So for calibration as well as for validation, we are still dependent on field measurements. Also, for certain applications like subsurface analysis, etc., we are still dependent majorly on field measurements. Okay, so now knowing the what and why part of it, the next question before is how to do remote sensing. So we have let's try to make this process happen. I've put here some components of remote sensing. A is the source. So the source of illumination, the source that illuminates your target, that serves as the source of energy. Here I've taken it as sun. It can be a natural source, it can be an artificial source also. So first thing is the source that you require. Second thing that you require is the target. What target you want to sense? You have to know about it. And then your platform and sensor. You have to carry your sensor, a detector, on some instrument, on some platform. So together you have a platform and a sensor carried over it. Okay, so you have source, you have target, you have platform and sensor combination. And then once the data is acquired on board, you have to disseminate this data to the ground receiving station. We call it as ground receiving terminal or GRS, ground receiving station. In India, we have this at Shadnagar. So this data is related to any antenna which is capturing the signals from the line of sight of your platform and sensor. Then once this information is downlinked here on GRT or GRS, this information is then tried to free from errors that are known to the PIs of the project. That means the ones, the vendors which are going to give you the data, they try to free the data out of some errors which are already known. Plus, they try to also give the transform the data into some usable format. Okay, so here you do some pre-processing of the data, and once the data is pre-processed, you cater to different applications. This is given to different users. So you have a source, you have a target, you have a platform and a sensor combination. You have a ground receiving terminal. You have to do some pre-processing of the data, and then you give it to different users. Now here, for Earth observation purpose, it's not that the light is just coming through vacuum only. The major part of the light travels through vacuum, but then there is a thin sheet of gases and particles around the surface of Earth, which is called atmosphere. But this interaction with atmosphere is not actually wanted. However, we can't do away with it. So this interaction with the target first happens with the atmosphere while incoming, and while outgoing, it also has to first interact with the atmosphere before it reaches the sensor. So it's a two-way interaction, both while incoming as well as while outgoing with the atmosphere. Now I have put here three rays, one solid red, the another the purplish, and the third is dotted red. So what's the difference between all these three is, number one, you can see for red solid line, you can see that light is incoming from a source, hitting the target. Part of it is getting reflected to the platform and sensor. Okay, so this is called a reflective type of remote sensing, where you receive the reflected portion of the electromagnetic spectrum by the target to the sensor, right? You look at the another arrow, which is again red but dotted. Here, this target itself is acting as a source. Now, it's like that. Suppose I switch off all the lights in the room and I want to take a photograph. So what options do I have? Even if I don't have a flash in my camera, what options do I have? I still want to take a picture. So that time I can use night vision cameras or spy cameras. What do they actually do is they sense the thermal radiations which are emitted by the objects, and then they try to map this thermal radiation in the form of an image. Okay, so every target, everything in this universe above 0 Kelvin is emitting some sort of energy. Okay, for Earth, these emissions are maximum in the thermal radiation, thermal region, thermal infrared radiation. So if you have a sensor which can sense these emitted radiations from the target itself acts as a source. So this type of remote sensing is emissive remote sensing. The first one which I talked about was red solid line, where you sense the reflective portion of the energy from the target. The another one, the red dotted line, which I'm just discussing, is the emissive form of energy which is coming from the target. Both these types of remote sensing are called passive remote sensing. So the other type of remote sensing which is shown here in the form of purplish double arrows here is active remote sensing. It can be understood in a simple way like this. Suppose in that same dark room which I just talked about, if I have a flash in my camera, I can use that source of light on the platform itself. The platform is now my mobile handset. It's also carrying the camera, but it is also carrying the source. So if I can use the source on the platform to eliminate the target and then receive the backscattered energy from the target, this type of remote sensing is active remote sensing. So difference between passive and active remote sensing is, in the passive remote sensing, I'm not using any source on the platform to eliminate the target. In active remote sensing, I'm using a source on the platform which first eliminates the target and then receives the backscattered energy. I hope you all have heard of LiDARs or radars, etc. These all work on the principle of active remote sensing, where the target is first eliminated using the source which is carried on the platform, and then the backscattered signal is recorded. So red solid and red dotted are the examples of passive remote sensing. This purplish is an example of active remote sensing, right? So now, why one should use active remote sensing? You have to bear an additional cost of a source also on the platform, because now you can work day and night, and plus the in the microwave region, if you are working, these can penetrate easily through the clouds. So that is an additional advantage. And plus, you can also control the elimination of the target through the platform itself, right? So both type of remote sensing processes do occur, passive as well as active. Maybe in the later part of your classes, you'll be getting exposed to different types of sensors which are used for disaster management, which will include both the active as well as passive remote sensors. Now we have learned about what, why, and how part of remote sensing. I hope that's clear to you. If anything which you would like me to repeat, maybe given as queries in the interaction session so that we can have more discussion on that topic. Right, so now coming to what actually are we sensing? We are sensing the electromagnetic radiation. Why electromagnetic radiation? Because we have to sense that type of energy which can sustain itself in vacuum. Okay, and that essentially is in the form of electromagnetic radiation. So if you plot the electromagnetic radiation in terms of its wavelength or frequencies, you can see that you get electromagnetic spectrum, starting with cosmic rays, gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. Shorter wavelengths are associated with higher frequencies and therefore higher energies. and longer wavelengths are having lesser energy. For Earth observation, we are mainly concerned with ultraviolet, sometimes for atmospheric remote sensing mainly, but in the major part of it, we are working in visible, infrared, and microwaves. Okay, let's try to understand how the interaction of electromagnetic radiation takes place with the Earth's surface. Now, this I am talking about a reflective type of remote sensing, where the incoming energy is hitting the target, part of it is reflected, part of it is transmitted, and part of it is absorbed. Okay. In reflective remote sensing, we sense this reflected portion of the spectrum. But in the emissive remote sensing, we sense this absorbed energy which is re-emitted because no object is a perfect source or sink of energy. So it can't be actually absorbing the energy. Okay? It has to re-emit it depending on its temperature. It attains thermal equilibrium and then some amount of radiation is emitted from the target. And if you are able to sense that emitted portion of the energy, we are working in the emissive type of remote sensing. Now, there is another concept that you'll be coming across very frequently is spectral signatures. Now, if you're looking at the reflective remote sensing, we want to know the reflectance behavior of different targets. Now, every target has a unique identification, which is given in terms of its spectral reflectance. Mind it, I'm talking of only the reflective remote sensing. If you are working in emissive remote sensing, this definition will change in terms of emissive, right? So, in the reflective portion of radiation, the spectral signatures are defined as the variation of spectral reflectance with respect to wavelength. So every target, every feature is associated with a different spectral signature. For example, vegetation will have a different spectral signature compared to water. Now, within vegetation also, wheat will have different signature compared to rice. Within rice also, rice of basmati A and non-basmati will have different spectral signatures. Within basmati also, basmati varieties of different rice will have different spectral signatures. The point which I want to make here is every feature is associated with unique identification, which is called spectral signature. So in order to identify any object on the remotely sensed data, you have to reconstruct or you have to check the spectral signatures or you have to identify the target. You have to look at their spectral reflectance behavior. One common, very common example which we have depicted here is a healthy vegetation, which you will come across very frequently in remote sensing images, or soil, mainly either dry soil or wet soil or water. So major things that you can check out here is for water, any type of water it may be, in the infrared region of the spectrum. I hope you understand what is the visible portion, what is the infrared portion. If not, let me tell you here. The visible spectrum ranges from zero 0.4 to 0.7 micrometers. 0.7 to 3 micrometers, you have reflective portion of infrared radiation because here most of the infrared radiation is reflected. And from 3 micrometers to 100 micrometers, you have thermal infrared radiation. So in this part of the spectrum, most of the radiation, most of the IR is emitted. So when we are talking about reflective portion of electromagnetic spectrum, we are talking in terms of 0.4 to 3 micrometers in total. So this entire range is called optical range. All right. So you can see that any type of water it can be, but in the larger portion of infrared radiation, the reflective part of it, the reflectance is near zero. Okay, so any type of water you take, if you take any IR image, the reflective IR image, you will see all types of water to be dark. So if you want to distinguish between different types of water, you have to look at this portion of the spectrum. Similarly, if you look at vegetation, you can see that a healthy green vegetation, which appears green to your eyes, is having a bump here and then two dips here. These two dips are due to presence of pigmentation in the vegetation, which is essentially chlorophyll, and then xanthophyll, then beta carotene, etc. There are several pigments present in the leaves. Depending on which pigments we have in the leaf, those portions of spectrum will be absorbed more, and green here for green vegetation will be left for more reflection. So you see healthy green vegetation as having more reflectors in green portion of the spectrum. But if you look here at the infrared radiation, and in the near infrared part here, from around zero point 0.7 to around 1.2 or 1.3 micrometers, you can see that very large amount of reflection takes place from the leaves. This is due to the physiological structure of the leaf, the lower and the upper part of the leaf, and in between there are several voids. And due to this intracellular structure, you have large amount of reflections from the leaves, which leads to very large amount of reflectance in this portion. And then you have certain dips. This is due to the presence of moisture in the leaf. These are two minor dips, and then you have three major dips, 1, 2, and 3. So if you have a drier leaf, you will have more reflectance. If you have a moist leaf, you will have less reflectance. Similarly, if you look at soil also, if you have dry soil and if you have wet soil, a wet soil will have lesser reflectance. A dry soil will have more reflectance. The point here is more is the amount of moisture in the target, less will be the reflectance overall, especially in the infrared part of the spectrum. And then you can see that for any type of soil, the reflectance keeps on increasing, and then this type of behavior is seen in different types of soil. So if you look at the spectral signature of clay or loam or silt, these all will be different. Then from one type of clay to another type of clay, again, this will be different. From one type of sand with bigger particles and the other type of sand with smaller particles, the reflectance will again be different. So depending on what type of physical structure the target has, what type of chemical composition it has, what type of state it is in, the spectral signatures will be different. Okay, so to know the spectral signatures, to have a gist of it, you can visit the USGS library, where you'll have a large number of targets and the corresponding spectral signatures, which are recorded using field measurements. Okay. So with this, one more interaction that takes place, as I told you in the very beginning, that there is an interaction of radiation with the atmosphere also. So what happens is either atmosphere is made up of gases and particles. So two things happen. Either part of the energy which is incoming or outgoing is absorbed, so the signal is reduced, or a part of it is getting scattered. Scattered means it's getting redirected to different directions. So as a result of absorption of radiation due to atmosphere, we are left with atmospheric windows. It's like this. Let's try to understand with the help of this graph here. So you can see on the x-axis I've plotted the wavelength. On the y-axis you have transmission. All right, so transmission is increasing from 0 to 100% as you go up to the y-axis. So this graph tells you with increase of wavelength, how is the transmission of the signal affected. So at 0.3 roughly and lesser wavelengths, you know that ozone absorbs the ultraviolet radiation. So this dip is due to high absorption due to ozone. So more is the absorption, less will be the transmission. Similarly, you can see dips here, which are due to presence of different types of particles or gases in the atmosphere. For example, you have water here, water vapors and carbon dioxide, and again ozone absorption, etc. Major absorption dips are shown here. So if I want to make a sensor, okay, of electron to observe the Earth targets, which portions electromagnetic radiation should I choose? So if I choose this wavelength region, let's say from around point, I hope you are able to see the cursor where I'm moving, 6 to around 7 or 8 micrometers, then you can see that the transmission is near zero. So my sensor won't be able to record anything. So in order to the sensor to record something, some signals, you have to design your sensors in those ranges where the transmission is high, where the absorption is low. So those spectral regions where electromagnetic radiation is not absorbed much or is transmitted as a whole are called atmospheric windows. So due to absorption by different gases present in the atmosphere, we are left with only the atmospheric window regions if we want to observe the Earth targets. But on the contrary, if you want to observe the atmosphere or atmospheric components, then you can very well design your sensors in these regions also, because those are not transparent to the radiation, but carry the information about the type of gaseous constituent that is absorbing it. Okay, so for Earth observation, we should design our sensors in the atmospheric window regions. Plus, at every wavelength, you can see that the transmission never reaches 100%. So, both for incoming as well as for outgoing radiation, even if you are in atmospheric window region, some part of the energy is absorbed by the atmosphere. So this leads to diminishing of the signal. Signal is overall a bit reduced while it is incoming or it is outgoing. So due to absorption by the atmosphere, you have atmospheric window regions where you can design your sensors for Earth observation. Now, due to scattering of the radiation, scattering, as I said, is the redirection of light. So suppose the light was coming in this direction, it hit a particle or a gaseous molecule of the atmosphere. What happened is there can be several scenarios. So in this scenario where I've written this Rayleigh scattering, half of it got scattered in the forward direction and half of it got scattered in the backward direction. So here forward scattering is equal to backward scattering. This type of scattering is called Rayleigh and it is shown by very small molecules, atmospheric gaseous molecules. Now this, when I say small, small compared to what? Compared to the wavelength of light. So you have to compare two things, the size of the particle which is going to interact and the wavelength. So if the particle size is too small compared to the wavelength of light which is interacting, we are in the zone of Rayleigh scattering. If the size of the particle is comparable to the wavelength which is interacting, you are working in the my scattering region. Here, forward scattering is usually more compared to the backward scattering. So dust particles, smoke particles, pollution particles all fall in the range of my scattering. And both these types of scattering are also called selective scattering, because both these types of scattering are more prominent for shorter wavelengths compared to longer wavelengths. Okay, so the pollution effects or the effects of gases will be more prominent in the blue wavelength region compared to red or infrared radiation region. Okay, and then you have another type of scattering also, which is called non-selective. Non-selective because it is not dependent on the wavelength. Here, the size of particle is much, much bigger compared to the wavelength which is going to interact with it. For example, cloud droplets or cloud particles, large water droplets, these exhibit non-selective scattering. So all the wavelengths of the light which is composed of several wavelengths, all the wavelengths will be scattered equally. All right, so you call it as non-selective. So clouds usually occur as non-selective scatterers. Your pollution falls in the regime of my scattering, and gaseous composition is are all in the domain of Rayleigh scattering. So, what is the effect of scattering on remote sensing? The scattering leads to haziness. More is the scattering of the electromagnetic radiation, more hazy will be the signal that you receive or the image that you receive. So overall contrast of the image will be reduced. So absorption leads to diminishing of the signal, whereas scattering leads to poor contrast of the image. So both of the effects of atmosphere are to induce or introduce noise in the data. So I'll just summarize so far what we have learned. So we have discussed what, why, and how part of remote sensing. We have also seen the different electromagnetic radiation regions where the sensors are usually designed for Earth observation. We've also seen the spectral signatures, what spectral signatures are. We've also learned about active and passive remote sensing. And now we have learned about the effects of um, atmosphere on remote sensing images. Now we are coming to platforms and sensor concepts. So before I go into more detail of it, let us try to learn what resolution is. So I think I will take a break of 5 minutes here, and then we'll be back again online so that you have some time to just digest what I've just taught here in this half an hour or so. And we'll be back in 5 minutes soon. So, welcome back. As I said, that we'll be discussing some concepts of platforms and sensors. But before that, let's try to learn about some basic qualities of any image. Now, resolution. I hope you all have heard of this word resolution, but most of you must have heard it in terms of spatial domain. So, I'm telling you in terms of any generic term, it is the ability of any system to render the information at the smallest discretely separable quantity. So if I'm talking about spectral resolution, I'm talking about smallest discretely separable wavelength ranges. Okay, if I'm talking about spatial resolution, I'm talking in terms of smallest discretely separable distance or the spatial unit. If I'm talking it in terms of temporal resolution, then I'm talking about how frequently I'm going to visit the area. If I'm talking in terms of radiometric resolution, I'm talking about how finely I can slice down the energy levels. Okay, so let's have some overview of this resolution, how it appears. So for remote sensing images, you have now spectral, spatial, temporal, and radiometric, four types of resolution. All right. So whenever from now onwards you're looking at the resolution of any sensor, please mind it that what resolution are you looking at? Are you talking about spectral resolution or spatial resolution, temporal or radiometric resolution? Okay, so let me first discuss the spectral resolution. Um, so if I have an image or if I have a data and I have the data in one wavelength range only, or if I can have it in multiple wavelength ranges, if I can slice down the wavelength range into smaller intervals, this is what I mean in terms of spectral resolution. So suppose I have this entire visible portion of the spectrum. If I have only one sensor for sensing this entire visible region, I call it as single band image. Usually, visible band plus a portion of visible region plus a portion of near infrared region. This together, sensed by one sensor, is called panchromatic sensor. So, if you have a single band looking at this entire mostly visible range, you have a panchromatic sensor. If you have sliced it down into some intervals, let's say 100 micrometers or 200 micrometers each, then you are talking in terms of multispectral sensors. And if you further narrow it down to continuous or in fact contiguous overlapping wavelength regions, very, very narrow wavelength regions of the order of nanometers, 10 nanometers, 5 nanometers, we are talking in terms of hyperspectral resolutions. Okay, so panchromatic will have least spectral resolution, hyperspectral will have highest spectral resolution. Okay, so with this, the concept of true color composite and false color composite is also essential to be explained. So let me come to that. Now I have one picture displayed here in green, this, and the same picture in another color composite. So this is called true color composite. The features appears exactly similar to how we see it through eyes. But here you can see that these are trees or vegetation which is appearing reddish in color. This is in a standard false color composite. So why do we make different color composites and how do we make it more so is important to be understood at your level. So let me give an example of that. Now you look at the number of images I have displayed here. So I have 1, 2, 3, 4, 5, 6, 6 bands. I've taken them from Landsat sensor, and these are band number 1, 0.45 to 0.515. It's blue region. 0.525 to 0.605, it's green. 0.63 to 0.69, it's red. Then 0.75 to 0.90, it's near infrared. Then 1.55 to 1.75 and 2.09 to 2.35. These are in shortwave infrared and far infrared regions, respectively. So we have 6 wavelength regions or the 6 wavelength bands or spectral bands information available with us. So this I call it as 1, 2, 3, 4, 5, and 7. These are numbered in the similar way in the Landsat sensor itself. Okay. 6 is thermal band, so which is not included here. I'm talking in terms of optical domain. So I'm restricting myself to the range of zero point 0.4 to around 3 micrometers. That is visible plus infrared reflective portion of infrared. Now, if I hope all of you know that there are in any computer screen, the display system of that consists of color guns. So there are three color guns, blue, green, and red. So combination of information in these color guns yields different colors. I hope you know that the primary color theory is there where you mix different combinations of blue, green, and red, and you can form any other color by adding different combinations of them, but reverse is not true, right? So with this same principle, if I feed in blue information to blue color gun, green information to green color gun, and red information to red color gun, what I get is a true color composite, the exactly same picture which you see using your naked eyes. But what if I make 4 to come and sit in any color gun, or 5 to come, or 7 to come and sit in any color gun? I'll get some color composite, but not true color composite. So that will be called as false color composite. So let me take out 3 and make 4 to sit in the place of 3. So that will be again a false color composite. So there will be different combinations of false color composite. So internationally, we have a standard false color composite wherein you have this combination. Near infrared goes to red color gun, red goes to green color gun, and green goes to blue color gun. Here the colors of these bands show which color gun they are sitting into. Color guns are like chairs, okay? So you made 4 or near infrared to sit in red, red to sit in green, and green to sit in blue color guns. And this is how you'll get a false color composite, right? So you can get different types of color composites to visualize the image in different manners. But internationally, if you are looking at FCC, that's a standard false color composite with this combination on. All right. So why do you see different color composites? Because some information, some features are enhanced in certain color composites compared to other. Especially vegetation features are very much enhanced if you are looking at standard false color composite. Most of the information which we have is on the earth is either land or water. Within land, you have vegetated or non-vegetated. So if you are looking at enhancement of vegetation features, you can look at standard false color composites. All right. I hope that's clear. So now coming to spatial resolution. So spatial resolution is the smallest discernible distance on the space or on the ground which you can measure, right? So if you have you can see this picture taken in different spatial resolutions. This first one is having the poorest spatial resolution, and this one has the highest spatial resolution. So here you will have the 1 pixel size very small compared to the pixel size in this image. So let me show you some examples of from satellite data. This is taken from Indian satellite data AWIPS, which is at a spatial resolution of 56 meters. That means the x and y coordinates of 1 pixel, which is seen on the ground, is of the size of 56 meters. So whatever differences in features are there within this 56 by 56 will be recorded as single entity only. You won't be able to distinguish between different features within the same pixel of 56 by 56 meter size. However, if you go to higher spatial resolutions, let's say 30 meters, the same image now appears with higher amount of spatial information. Then 23.5 meters, then 15 meters, 5.8 meters, 4 meters. Now you can see that very nicely the details are coming up. You can see there are several agricultural patches, and then you have trees also, you have roads also. All these information is coming up. Even the kacha roads are also appearing very clearly at this resolution. If you further go down to 1 meter size of the pixel, you'll have even enhanced spatial features coming up. Okay, so there are several satellites which provide you high spatial resolution. Some of them are listed here: Iconos, Quickbird, Worldview, Cartosat, GeoEye, etc. So for different types of purposes, you look at different spatial resolutions. For example, for meteorology purposes or applications, it's sufficient to work at kilometers level. For oceanography, you can work around 500 meters or so. And for land use, land cover mapping or military surveillance, you'll have to go down to meters or sub-meters levels. Okay, so now coming to temporal resolution. As I said, how frequently you can visit the area determines your temporal resolution. If I can revisit the area very quickly or in a shorter spans of time, my temporal resolution of the sensor is higher. So again, it depends on what type of applications you are looking at. If you are looking at vegetation monitoring, it's sufficient to have information after every 5 days repeatability. If you're looking at meteorological applications, you will have to maybe monitor the changes every hour or every half an hour, etc. So temporal resolution becomes more important to be on the higher side when you're looking at meteorological applications. So different applications, as I said, it's not necessary for you to go for higher spectral resolution along with higher spatial resolution along with higher temporal resolution, because different type of applications can be met with depending on what type of application you ought to address. Okay, so even for meteorological purposes, for example, it's okay to work with higher temporal resolution but lower spatial resolution. Okay. So the last type of resolution which you come across in remote sensing images is radiometric resolution. So it's like that when the signal reaches the sensor, the signal which is coming from the target is in the continuous form. Okay, it's not one or two, it's continuously it's coming. So it's called analog signal. But when it reaches the sensor, we have an analog to digital converter here. It slices down the signal into different types of different levels of information. So if you have a low radiometric resolution, for example, like this, you have only 4 levels. So you have less amount of radiometric resolution, less amount of information. How good your spatial information be or how good your temporal resolution be, doesn't matter if you don't have a good radiometric resolution. Okay, so you should be looking at higher radiometric resolution because then the information at every pixel level will be nicely presented to you in different ranges of energy levels. Okay, so it is usually depicted in terms of 2 to the power n, where n is the number of bits. So it's usually given in terms of like 10-bit resolution. So that means there are 2 to the power 10 levels of slicing which is used, or quantization, we call it, quantization, which are used to quantize or to digitally convert the signal. Okay, so usually the data nowadays is coming with 12-bit or 16-bit resolutions. So you should be looking at higher radiometric resolution for your remote sensing data. Now, with this concept of resolutions, we come to platforms and sensors. So platform, as I already told you in the beginning, that this is a device to which carries the sensor. And sensor is actually the detector that gathers the data, that gathers the information, that gathers the signal. Okay, so there can be several platforms. It can be ground-based, it can be aircraft mounted, there can be space shuttle, you can have satellites. So for disaster management, you are mostly looking at satellite remote sensing, and orbit is the path followed by the satellite. So different types of applications require different types of orbits. So if you are having a continuous monitoring purpose, for example, you continuously want to have a look at certain place, you have a different type of orbit. If you want to have a global image mapping kind of application, you have to have a different orbit. If you want to have a selective imaging, you can have another type of orbit. So orbit will also depend on which type of application you are looking at. So majorly I am discussing some types of orbits. And this is equatorial, where the angle of inclination is the angle between the plane of the orbit and the equator. So if it is 0 or 180 degree, you have equatorial orbit. If it is 90 degree, you have a polar orbit. If it is less than 90 degree, you call it as prograde. And if it is little more than 90 degree, you have a retrograde. So these are inclined orbits. Now, here, if you look at the geostationary orbits, we are talking about equatorial orbits. Here, a satellite appears to be stationary with respect to the place on which you're observing from Earth. So, why it happens is because the orbital period of the satellite matches with the time of rotation of the Earth. So, it happens when you place or you fix the satellite 36,000 kilometers above the equator, okay, with orbital inclination 0. So, it's not like the satellite is stationary, it's like the satellite is continuously orbiting along with the Earth when we are looking from one particular place. So we call it as geostationary orbits. So obviously, how and which places you can use such satellites is like meteorological applications or communication purposes when you're continuously having your communication at a particular place. But the problem here is it will have limited spatial coverage because it will be continuously looking at a particular area. So you have to have multiple geostationary orbits if you want to cover you have to have multiple geostationary satellites if you want to cover larger spatial areas. Then comes the example of polar orbits. Now, if I want to cover the entire globe, I should be looking at orbits like polar or near polar orbits. For example, which is shown here, Earth keeps rotating from west to east, and satellite keeps moving from north to south or south to north, or vice versa. Okay. So this way, you can cover the entire Earth in different periods of time, depending on at which distance you have placed the satellite in the orbit. So here inclination for polar orbits is nearly 90 degrees, but usually we look at near polar orbits because at a particular angle of inclination, that is 98.7 degrees, what happens is satellite will cross the equator at the same time each day. So it will be synced with the solar time. Okay, it will be it's called sun synchronous. So every time you have the picture of the place, it will cross at the same local time. So illumination conditions will be similar, and you can compare the changes of different features with time. So most of the near polar orbits are sun synchronous, and you'll see that they provide you or they cross the equator at the same time every day. Okay. Then comes a concept of swath, which you will come across very frequently whenever you're looking at or browsing through different satellite features. You will come across a term called swath, swath or swath area. So if this is the entire this is the path of the satellite, okay, and if you look at this extent from the entire extent which is covered by the image of the satellite is called swath. So if you have it in both the directions for one picture, you have swath area. Okay. And now one important point here is, for example, this is one path covered by the one in the orbit. This is one path of the satellite. So let's say it is today. So second, when it goes back and the Earth also rotates from west to east, the second path comes here. Okay, so it is not necessary that the next path will be consecutive. Uh, the next adjacent paths would be consecutive. No, it is separated from the first pass by this much distance. Okay, so the adjacent pass might come after 1 day or 2 day or 5 days, depending on the orbital period of the satellite. Now then, there are different types of ground tracing. We have different type of scannings from the satellites. Very common across them is whisk broom and push broom. Whisk broom, as the name suggests, so it's across the track. So if the satellite is moving from north to south, whisk broom will be across this direction, east to west or west to east. Push broom will be in the same direction of the orbit or the path. So we can see this with the help of an example here. So if you are talking about cross-track scanning, what happens is you have a motor attached to the telescope or the sensor, and we have this telescope mirror, which keeps rotating with the help of this motor. Okay, so as the satellite goes in this direction, the scanning keeps taking place in the cross direction. So one common example of a cross-track scanner is Landsat series of satellites, which were designed across the track. But nowadays, we generally have push broom sensors, which are working on the principle of CCDs, charge coupled devices. So for each pixel, you have one CCD. So you have an array of different CCDs. If this is the entire swath, for every pixel, you have one CCD. Not only one-dimensional arrays of CCDs. Today we have multi-dimensional arrays also. This example is for single-dimensional CCD array. So as the satellite moves from this direction to this, as the track arrow is shown, the scanning also takes place in the same direction. So this pixel is scanned in this manner, another pixel is scanned parallelly, etc. Okay. So there are some examples of land imaging satellites, common land imaging satellites, Landsat, Spot, IIRS, NOAA, Iconos, Cartosat, etc. And those were the satellites. But on the satellites are kept the sensors, and the names of sensors can be are depicted. Some names are depicted here: multispectral scanner, thematic mapper, then MODIS is there, WIFS is there, AWIFS is there, etc. So different sensors are there on different satellites. So with this, I wind up. So what we have learned in today's class is the basics of remote sensing, the basic concepts of it, and the basic concepts of platforms and sensors. So maybe after 5 minutes or so, I'll be taking up some queries from your side. We'll be back again in 5 minutes.